Hello, ladies and gents. We're going to talk a little bit about how the depth of a collection of fluid is going to affect pressure. Basically, the higher the column of fluid, the greater the amount of pressure that it is going to exert. And who does this affect? Everything from mountain climbers to scuba divers, cooking, and everything in between. So let's talk a little bit to begin with scuba divers. Basic open water divers, first license that people get diving, they can go down to about 18 feet, somewhere in the neighborhood of about 6 meters. Advanced open water divers, 100 feet, about 30 meters. If you're going to go down further than that, world record is right around 1,000 feet, about 300 meters, and this is with a great deal of air tanks. This is with a great deal of time to allow for pressure differentiation of those gases inside your body, and very, very complicated things. Anything much deeper than that, you're definitely going to need some sort of a hard suit to protect the human body, or a small submersible sub, because the human body can only withstand external pressures of a certain quantity before it just is going to collapse. Altitude itself on planet Earth is going to affect atmospheric pressure. And it depends on the weight of the air above you. So if you happen to be down at sea level, it is the weight of the column of air above you is a large quantity of air. And so this is going to represent a very, very high pressure. As you get a little bit higher in elevation, where I live happens to be about 1,000 feet above sea level, not terribly high, but in the Midwestern part of the United States, a little bit lower than at sea level itself. But by the time you get way up into the Rocky Mountains, we're talking Colorado Springs, we're talking Denver, or even points higher, you are somewhere about 5,000 feet or more above sea level, and the weight of the column of air from the top of the atmosphere, which is somewhere around 55,000 feet, to the land, you are now a much shorter column of air. That means much lower atmospheric pressures, because it is that weight of air on top of you that makes or produces air pressure. So what are some of these effects of high altitude, low pressure? Well, one of the things it affects is boiling temperature. When a liquid boils, what happens is the molecules inside of that pot of liquid have got to have enough kinetic energy to break free of the interparticulate forces between the other water molecules. And if this little water molecule has enough energy, it can go bing, and it can escape from the pan and turn into a gas or a vapor. Well, if you go to a higher altitude and there is less air pressure pushing down on the pan, these molecules can escape with a smaller quantity of kinetic energy, and that means it's going to occur at a lower temperature. So what does that mean? Well, that means it's going to affect cooking. If you have ever looked at the side of a package of, I don't know, cake mixes or a whole bunch of prepackaged things, you may notice high altitude baking directions. And high altitude baking directions often say you've got to cook food longer. Why do you have to cook the food longer? Because instead of water boiling at 212 Fahrenheit, you get higher and higher and higher. Food is going to boil at a lower and lower and lower temperature. And what that means is to get to the same quantity of doneness, you have to cook it for more time. And there sometimes are other tweaks to high altitude directions, but more time is definitely one of the things you're going to see. Now, a pressure cooker happens to be the opposite effect. The old-fashioned pressure cooker that you put on the stove with a handle that you lock in place, what this would do is prevent these molecules from escaping by having huge, massive vapor pressure from the escaping steam holding all the molecules in. So before they could turn into a steam, they had to have huge kinetic energy, lots and lots of speed. And what that meant is the boiling temp would be very, 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 very high, and it would be much hotter. Because when something is cooking or boiling on an open pot, it will not get any hotter than boiling temp. But if you put it in a pressure cooker, you can actually get it hotter and hotter and hotter. And I love this little chart right here. In a regular, you want to cook a whole chicken, it's going to take about 60 minutes. In a pressure cooker, about 15. Brown rice takes a long time to cook, 50 minutes on the stovetop, 20 minutes in a pressure cooker. Black beans, again, takes a long time to cook those, about 15 minutes in a pressure cooker. Now, pressure cookers, a lot of people don't have these anymore unless they do canning or things like that. The thing that has replaced pressure cookers in the hearts and minds of a lot of Americans are the Instant Pots. The Instant Pots are an electric pressure cooker. And what it does is it locks this lid in place, lets the steam build up inside of the pot, makes this get hotter and hotter and hotter by having very, very high pressures, and it makes the cooking temperature much, much greater, which makes cooking time much, much shorter. Things like, this is just crazy to me, asparagus 1 to 2 minutes, peas 1 minute, potatoes 7 minutes. We're on the stovetop. It's going to take me 20 minutes to boil potatoes. If you're going to cook something like a whole chicken, 25 to 30 minutes. So you're cutting cooking times in half. A pot roast for me to do it is at least like an hour and a half, 2 hours, and you're definitely cooking things much, much faster. Now, when you get to those high altitudes, up in the mountains, there is much lower atmospheric pressure. It also means that at those altitudes, air is going to be less dense, and less dense means that there are going to be less oxygen molecules per breath that you take. The U.S. Olympic Training Center happens to be in Colorado Springs, 5,000 feet or so above sea level. Now, that is not by accident. One of the advantages of having our Olympic Training Center at those high altitudes is because of the fact that if athletes are training in a situation where they have lower oxygen environment and then they go and compete down at sea level at certain games that are down in cities by the sea, they are going to have blood that is more highly oxygenated, and it is a natural way to enhance the ability of the athletes. So the fact that we've got some high mountains in our country helps our athletes. Fluids naturally want to move from high pressure to low pressure. And one of the places where this intersects this concept of going higher in the atmosphere means lower pressure is when you go up in an airplane. So you're in an airplane down on the tarmac before you take off. That looks like a roller skate. Sorry, it's supposed to be an airplane. And you go up into the sky. And when you're up in the sky, there's a lower atmospheric pressure. You're down in the ground. It's a higher atmospheric pressure. If you've ever been up in an airplane or a very fast upward moving elevator, what happens sometimes is your ears pop, and it's highly, highly uncomfortable. And what's going on is this. You have a high pressure in your head and in your auditory canals, eustachian tubes, all of the gaseous airways inside of your head, and you've got your little eardrums out here. Well, if you go quickly to a low pressure, your inside of your head and your outside of your head have not had a chance to equalize pressure. So there is a low pressure outside, high pressure inside. Gases and fluids naturally want to move from high to low pressure, so your little eardrums are bulged out and they're very, very uncomfortable. So what do you do to make your ears pop? You swallow, you chew gum. If you have a baby, you give the baby a bottle so that it's a happy little baby and not crying and squawking all the way on takeoff and then again on landing. Another couple examples of fluids moving to high or low pressure is if you fly, and you ever fly into an airport into a city that has a much higher elevation than you are used to. Let me give you an example. This happens to be Denver, a picture of Denver Airport. Denver, again, the mile-high city about 5,000 feet above sea level. Well, this is not a terribly glamorous example, but it does happen, and it has happened to people I love. If you are a lowlander from not up in the mountains, you have internal gases in places like your bowels. And you go to a high city, what happens is these bubbles expand, and the expanding, oh, I'm going to draw a person here and it's not looking good. And as these bubbles expand, they have to come out. And where do they come out? They come out of your body as flatulence. And so sometimes when you fly into a higher elevation city, takes a day or two for your digestive system to calm down and not be so gassy. Food on airplanes. If you buy some snacks before you get on the plane and you get up to 30,000 feet or wherever that plane is cruising and you look at your bag of Doritos and you go, oh my gosh, it's all puffy. These were packaged down at sea level. Well, down at sea level, under a high amount of pressure, the Doritos bag wasn't looking like a big puffy pillow. It goes to a low pressure environment up here and the high pressure inside the bag surrounded by the low pressure, and it has a tendency to puff outward. Long ago in my life, I flew an awful lot for business, and it seemed like I was always on an airplane about breakfast time, and I was always getting yogurt. And all my little yogurt cups I would get on the airplanes were always, their lids were always bulged like this. And I would open the little tinfoil lid of the yogurt, and it would always go, and it would spit all over my clothes. Well, I wasn't bright enough. It took me a couple times before I realized it was exactly the same thing that was happening with the Doritos. It was the gases inside the cups that were expanding and then pew, kind of popping out when I opened the cups. At the end of this video, I'm going to throw on my playlist a couple really cool videos showing big, crazy things imploding due to air pressure. One of the classics is large tanker cars, railroad tanker cars, and these are, the air is literally pumped out of them. And when this gets to a very, very low pressure inside, high atmospheric pressure just from the weight of the air on top of them, these things implode, and they're pretty dramatic. These are not fake pictures. These are real things that have occurred. And it gives you a real dramatic example of how powerful air pressure can be. Two small things about air pressure before we finish this video, and that is to talk a little bit about straws and siphons. Think about what's really going on with a straw. With a straw, you are in your mouth, you are actually creating a low pressure. Now, it's not that you're sucking the fluid up into your mouth. What you're doing is you're creating a little bit of a low pressure by creating a higher velocity gas in your mouth, and then the atmospheric pressure, the air around your cup of soda, is pushing down on the rest of the cup and forcing the liquid into your mouth. Pretty cool stuff. Siphons are kind of magical things. We used to have fish tanks in our life, and if you had to empty a fish tank, you're not supposed to lift big heavy fish tanks even if you could. So how do you empty them? A piece of hose. Put the hose on the bottom of the fish tank. Make sure the other end is in a bucket or something that is well below it. And then to get the siphon started, kind of gross, but what you'd have to do is you'd have to suck on this end and create a low pressure. Once you created a low pressure down here, the liquid from the tank would flow through the hose, even though it was a weird and crazy shape like this. And then the atmospheric pressure up here would push the water out the hose, and it would drain the tank. Siphons are a wonderful thing. If you've never tried siphoning anything like a fish tank or a tub of water, please try it, because like I said, it's kind of like magic. That works really, really slick. All right, that will do for this time. We'll come back next time with an equation.